focusing on delivering value and interpreting global bestsellers. Hi, this is Sally's Book Club. Today we're exploring the book The Lethal Companion. This lethal companion refers to bacteria, omnipresent yet often unnoticed in human life. But when you get mildly ill, you truly feel bacteria's power. Bacteria cause diseases like tetanus, pneumonia, tuberculosis, and even trigger pandemics. The Black Death wiped out half of Europe's population in the Middle Ages. Aren't bacteria truly lethal companions? So how can we protect ourselves? The book's subtitle, Surviving in the Bacterial World. Author Jessica Snyder Sachs is an American science writer who taught scientific writing at NYU. She specializes in health, medical topics, revealing unprecedented insights about bacteria in this book. Reading this will reduce your germophobia and even foster appreciation for bacteria. When encountering topics like antibiotic resistance or superbugs, you'll make informed judgments. I'll break this into 3 parts about surviving the bacterial world. Part 1, understanding our bacterial environment. Part 2, humanity's battles with bacteria, methods and outcomes. Part 3, coexisting with our lethal companions, future directions. First, let's examine our bacterial environment. Don't panic. Not all bacteria are harmful. There's good and bad. Beneficial bacteria like lactobacillus in yogurt aid digestion. Harmful bacteria need no introduction. Every disease-causing germ counts. When do bacteria first colonize humans? The answer, before birth. During pregnancy, the birth canal increases lactobacillus. These bacteria colonize baby's mouth during birth, followed by millions of bifidobacteria from breastfeeding. These pioneer bacteria then begin recruitment efforts, selecting other microbial immigrants like Streptococcus salivarius, Fusobacterium, and Streptococcus mitis. This colonization process completes within baby's first week. Streptococcus salivarius naturally combats bad breath, while other bacteria enhance oral diversity. Overgrowth of any strain causes issues. For example, excessive Streptococcus mitis may lead to infective endocarditis, hence needing balanced microbial coexistence. Where do these early colonists originate? Primarily from maternal oral flora. Then siblings' mouths, bacteria silently transfer through kisses or shared utensils. Another microbial surge occurs during teething, welcoming Streptococcus sanguinis and mutans to dental surfaces. One particular bacterium becomes hyperactive in puberty's sebaceous glands. Most dislike this resident, Cutibacterium acnes. About 100 billion bacteria inhabit skin surface, equivalent to pea-sized mass when aggregated. How many reside in digestive tract? 15 trillion, roughly filling a soda can. We've coexisted with countless bacteria long before 20th century discoveries. Human-bacteria relations began conflictually through epidemic battles. Part 2, our historical warfare with bacteria. Bacterial attacks manifest as epidemics. Thus, our struggle began with disease containment. 17th century Europe saw 2 contagion theories emerge during plague outbreaks. Miasma theory proponents believed poisonous air caused infections. People nailed shut patients' doors, with passers-by burying noses in flower bouquets hoping to purify toxic air. In mid-19th century Europe, upper classes feared slum miasma infiltrating their neighborhoods. They upgraded sewage systems and promoted public water networks. Oh, these early public health measures broke waterborne disease cycles. The alternative contagion theory suggested disease spread through contact, germs being the cause. In 1876, German scientist Koch proved pathogens could infect healthy animals. His rival Louis Pasteur demonstrated microbes can't generate spontaneously. Pathogens must transmit externally. He later proved heat could sterilize food or waterborne pathogens. This led to pasteurized milk, heated to 60 degrees Celsius plus to kill germs without affecting quality. Koch and Pasteur proved specific bacteria cause specific diseases. Pasteur developed vaccines, crucial victories against epidemics, but vaccines prevent rather than cure infections. Researchers sought complete bacterial eradication through total warfare. In 1885, German pathologist Ehrlich proposed magic bullet drugs, targeting bacteria without harming hosts. His 1908 syphilis drug, salvarsan, paved way for sulfa drugs, early antibiotics. In 1928, Alexander Fleming observed penicillin mold killing staphylococci. Thus, penicillin entered human history. Next 2 decades became antibiotic golden age, but were they truly magic bullets? Did humanity finally conquer bacteria? Absolutely not. The war continues, new challenges emerged. Compromised immune systems and antibiotic resistance. Let's begin with the first aspect. Improved public health awareness has made hygiene, chujul insik, common knowledge, crucial for disease prevention. However, excessive cleanliness in developed nations correlates with rising allergies and asthma. These conditions were rarely heard of historically. You might blame air pollution or modern stress, but research shows no conclusive evidence supporting those theories. The root cause may lie in malfunctioning immune systems. Our ancestors' exposure to microbes helped immune systems evolve. Modern sterility disrupts this balance. Allergists found consistent microbial exposure trains immune responses. These microbial old friends fall into 3 categories. First class, 1, environmental bacteria. Second, human commensal bacteria. 3, intestinal helminths. These companions co-evolved with humans over millennia. Immune tolerance develops through recognition of these familiar organisms. Allergies indicate tolerance failure. Without tolerance, immune systems attack harmless substances, even body's own cells. This tolerance deficit likely stems from insufficient childhood microbial exposure. Abnormally low bacterial colonization during development. Our environments have become excessively sanitized. Now, to the second challenge. While antibiotics combat infections, they accelerate bacterial evolution through resistance. Antibiotic pressure selects resistant strains that rapidly dominate populations. This pattern emerged with first-generation antimicrobials, sulfa drugs, 1930s, and penicillin, 1940s, faced resistance within years. Moreover, this antibiotic resistance can rapidly spread across bacterial species. Despite new antibiotics, bacteria evolve continuously, giving rise to superbugs. Imagine pathogenic bacteria as bronze warriors, drug-resistant strains as silver warriors, and superbugs as golden warriors. How does antibiotic resistance develop? 1951, Wisconsin University research proved pre-existing resistant bacteria at 1/10 million ratio. Antibiotic exposure eliminates non-resistant strains, allowing survivors to dominate. This isn't gradual adaptation. Antibiotics accelerate bacterial evolution through Darwinian selection. You might think, use dual antibiotics against rare resistant strains for guaranteed elimination. The medical community once shared this naive assumption. Bacterial evolution outsmarted such strategies. The late 1940s to early 1950s saw multi-drug resistant strains emerge in hospitals, transforming previously treatable infections. What caused this alarming shift? Resistance genes spread horizontally between bacteria. 4 transmission methods exist. Plasmids, extrachromosomal DNA carrying resistance genes, were first discovered. Bacteriophages, bacteria infecting viruses, can transfer resistance genes during infection cycles. Jumping genes, transposons, relocate between chromosomal locations like genetic nomads. With precise genetic navigation, you can even transfer between different bacteria. This genetic exchange creates a bacterial superorganism sharing adaptive traits. Finally, bacteria can directly uptake genetic material without vectors. Antibiotic overuse has turned human bodies into reservoirs of drug-resistant bacteria. Tens of thousands suffer antibiotic-resistant infections annually in the U.S. alone. Similar crises occur globally. Pharmaceutical companies abandon antibiotic research due to rapid obsolescence. Developing new antibiotics risks creating more dangerous superbugs. Traditional antibiotic approaches can't solve modern infectious challenges. How can humanity coexist with these lethal companions? First step, curb antibiotic misuse. Physicians must avoid unnecessary prescriptions. Viruses don't require antibiotics. Second, optimize treatment duration scientifically. Third, preserve beneficial microbes by avoiding broad spectrum antibiotics when possible. Broad spectrum antibiotics act like shotguns, destroying diverse bacteria indiscriminately. Narrow spectrum antibiotics target specific pathogens like precision snipers. Narrow spectrum options better protect microbiome balance. Ideal protocol: start with narrow spectrum, escalate only if ineffective, requires pathogen identification and sensitivity testing. Practical challenges exist. Culture and sensitivity tests take days. Patients expect immediate treatment, creating diagnostic pressure dilemmas, especially in emergencies. Rational antibiotic use requires rapid, accurate diagnostics. 2005. Dr. Edwards at University of Florida used genetic amplification to rapidly detect group B streptococcus in childbirth. The entire process from specimen collection to analysis takes just 2 minutes, with results available within an hour. This allows antibiotic-free delivery for mothers without targeted bacteria. Additionally, switchable drug designs minimize antibiotic side effects. For instance, adding intestinal protective enzymes deactivates residual antibiotics before reaching colon microbiomes. Another approach creates antibiotic disguises harmless to beneficial flora but lethal to pathogens when activated. And where, beyond antibiotic improvements, humanity explores alternative solutions. Vaccines present lower resistance risks compared to antibiotics. Vaccines activate targeted immune responses. Unlike antibiotics' indiscriminate destruction, advances in immunogenetics may enable vaccine superiority over antibiotics. Scientists explore preemptive microbial engineering, replacing problematic strains with beneficial ones. This bacterial replacement therapy utilizes probiotics. 1970s Canadian urologist Dr. Bruce observed vaginal E. coli correlating with recurrent infections, unlike lactobacilli-dominated microbiomes. The lactobacilli effectively block invasive bacterial colonization. This explains yogurt probiotics' gut health benefits through microbial competition. Beneficial bacteria occupy niches, preventing harmful strain establishment. Deepening microbial understanding guides harmonious coexistence strategies. We need neither excessive avoidance nor panic. As microbiologist Saylor noted, sterile environments impair human biological functions. Learning personalized coexistence with microbial ecosystems optimizes human health. All right, that's our exploration of the lethal companion for today. Reading notes are below the audio. Catch you next time with another great book.